Greetings, friends. Welcome back from spring break. I hope you had an enjoyable one. We are going to get right back to it. It is Tuesday. It is April 8th. So we've got a couple of things on the schedule that I'd like to let you know about. And so I will remind you about PLC 9, which is going to be due Friday. And it's in its usual format of a quiz style PLC. So that is up and running, and it is on interference, which is what we are going to be talking about for the next few days. We finished off talking about the double slit on Thursday before break. So homework number 5. Is it homework number 5? Well, we've got homework. That's going to be due Thursday. That is April 10th. We will have the usual quiz associated with that homework set and be ready to go on Thursday. So I think we should be relatively good to go on that. I'll do an example today, and we will get through some reflective interference tomorrow. We'll do a little bit more on thin films, and that should set you up and be good. Now remember, the homework is due by midnight on Thursday, so that should give you enough time, as we will be finishing up the material today and tomorrow, so that'll give you the rest of Thursday to finish that homework off. So we left off talking about the double slit experiment and the conditions for constructive and destructive interference. So what I'm going to do is go through and do an example here. And I apologize for my voice. I am a bit croaky for some reason. I don't know the reason, but nonetheless. We'll try and quell that. Okay, so let's take a look at an example in which I have a two-slit experiment. And we're illuminating it from the left here with light. What we're going to do is we are going to have one wavelength coming in, incident from the left, and look at the pattern that's subsequently formed on the screen over here. We're going to then switch the wavelength to a different color wavelength, have that come through, and then we're going to see if we can calculate differences in what the pattern looks like on the screen. Now, before we start this, I want to remind you in these problems, the drawings are always out of proportion. The reason is the slit spacing is typically very small, okay? And the screen distance is usually much larger. So you might be thinking of something on the order of tenths of a millimeter of spacing between the slits here. And maybe a meter or two or something like that, distance between the screen. So that is an order of more than 1,000. And I'm not going to be able to represent that here. What that does for us is it gives us the opportunity to use the small angle approximation. And so what I'm going to do in this example is I'm going to set it up, and we're going to look through how to use the small angle approximation in setting up the two-slit experiment. All right. So let's suppose I have a screen over here. And the pattern on the screen is due to the interference of the light. Now, I have not mentioned much about the light, but the light coming in will typically be laser light. Reason being, that is the easiest way for us nowadays to get coherent light. What does coherent mean? It means when the light leaves the slit, top or bottom, they are starting at exactly the same place in their waves, okay? So that means if I start by drawing, maybe I have an interference up here, maybe I have a bright fringe up here, say. All right, if I have a, up there somewhere, like so, I do this. What this gives me the ability to do is draw the waves on top of these rays. This is typically how I would encourage you to draw the two-slit experiment. Like so, right? Notice how both waves are starting at exactly the same. Basically, I'm just drawing a sine wave here. But because this is coherent light, it doesn't matter where they start on the wave, they just start at the same place because all the waves coming in from laser light are coherent. Okay, they swim together in phase. And that's a special property of laser light and does not apply to regular room light like this or regular natural light. This is a special property of laser light, okay? So, what I want to do here is say that I start with lambda 1, and then we switch to lambda 2. In lambda 1, I have a pattern here, and suppose I'm looking at a bright fringe up here, and suppose this is the n equals 3 bright fringe. In other words, that means that my central bright fringe is about here. And that's the indication that I have 0 path length difference between the two waves here, right? That's what the M number is. It's telling you how many wavelengths are you expecting in the path length difference. So here I have 0 because I have 0 wavelength because there is no path length difference going straight across. I'll have a dark fringe here, and I'll have a bright one here, dark one here, and then another bright one here, and then a dark one there. So I've got 3. I gotta go 1, 2, 3. So we're gonna go 1, 2, 3. This is n equals 2. This is n equals 1. All right. So those are the bright fringes, and in between is dark fringe. Is a dark spot here. Okay. So what we do is we're going to measure from the central axis here up to this spot right here, and we're going to call that y. All right. Now, remember, again, I am going to emphasize, my drawing is not to scale. So this distance could be tenths of a millimeter. This distance could be millimeters. This distance could be thousands of millimeters. All right. So it does not look like necessarily I can do a lot of the things that I'm about to do, but because I'm going to have a small angle, I can take these approximations that I'm going to show you. Okay, we're going to call this distance little d here, and that's fairly standard. That's the slit spacing. Okay, capital D is the screen to slit distance, and y will be the distance on the screen from the central axis where I'm going to measure to find the third bright fringe in this example. All right, the question is, once I've set up this situation with my lambda 1, I'm now going to change to lambda 2. And the change in the pattern on the screen is going to cause my bright fringes to be in different places. So my question then is going to be, what's the difference in the on-screen position of the third bright fringe? All right, going from a lambda 1 to a lambda 2 situation. All right. So I'll call this I'll call this y1, which corresponds to lambda 1. And then when I get lambda 2, I'm going to get a different pattern. So one question you might ask yourself is, can I, by reasoning and not by using mathematics, convince myself that I should find an expansion of the pattern on the screen if I increase the wavelength? Okay, so suppose that I'm going to use a wavelength which is smaller here in lambda 1 and larger here in lambda 2. What do I expect to happen to my y? And I think you should be able to convince yourself that y should increase when I increase the wavelength. And you should be able to do that without mathematical means, okay? So when I get to y2, I'm just going to draw over here like this. I'm going to put that up here. Okay, like that. Maybe my second bright fringe is up there. My question is, I want the difference in those two positions of the third bright fringe. Okay, so that's what I'm aiming for. Basically, that's called delta y. All right, so let's take a look here. y2 minus y1. All right. Now, from last time, we know how to find the path length difference. We know that the path length difference, which I'll just abbreviate as PLD here, is equal to little d times sine theta. Theta is the angle that these rays are making with the straight across. Right, like that, and like that. This is theta. This is theta. Now, clearly they can't both be the same theta. And that's if you look at this drawing. But remember, this drawing is not to scale. This drawing is wildly out of proportion. When I get to the real distances that are involved here, these angles are so close that they're different in at least the second order. All right? So it doesn't look like it. And plus, you would say, well, these rays are not parallel because they do eventually cross up there, so they can't be the same angle. Yes, I understand all that. However, I'm telling you, this drawing is out of scale. And so it looks like it from this situation, but when you see an actual setup like this, you would realize there's going to be really small angles and they're going to be very, very close to each other. And therefore, we can basically approximate these as being at the same angle. So we talk about the path length difference as being d sine theta. Now, in the small angle approximation, we can use a substitution here for sine of theta. Now, in small angles, we have the ability to say that the sine and the tangent are approximately the same. So in the small angle approximation, sine theta is approximately the same as tan theta. And that's approximately the same as the angle. Now, make sure that angle is in radians. Okay? That cannot be a degree angle. That must be a radian angle. Okay? So, what I can do here in the path length difference is say that I have d sine theta, so I could swap that out with d tan theta. Well, if I look at my big triangle here, tangent of theta is fairly straightforward. It's y divided by d. And so I could approximate this as being y over capital D. And since I know I'm looking at the third bright fringe, then that tells me that there are three wavelengths in the path length difference. Okay. Now, I have in constructive interference, I have an integer number of wavelengths in the path length difference, okay? And if you're not certain on that, go back and watch the last video where at the very end, where we're dealing with the path length difference. Okay? So, in this situation, I know I'm looking at the m equals 3 bright fringe, and therefore I know I've got 3 wavelengths in the path length difference, and therefore I can use this situation here to solve for a y, and say that y is equal to m lambda times capital D divided by little d. Is that right? Y is going to be m lambda times capital D divided by little d. Yes. All right. Okay. Now, if I want the delta in y is going to change because I am altering the wavelength, not because I'm altering the slit spacing or the screen distance or anything like that. It's changing because I have a different wavelength. So if I look at a delta y here, imagine doing a pseudo differential on this thing. If I want to differentiate this thing and find out what is y's change going to depend on, I would have only the lambda to pick out as being the thing that's going to cause a change in the y. So I should be able to rewrite this as m times capital D over little d times delta lambda. In other words, I don't have a delta of anything else, so it's going to be a lambda in this case. I can rewrite that, since I'm looking for the difference in y3, that means my m is equal to 3, and this lambda I could rewrite as lambda 2 minus lambda 1. So in this case, it's 3 times capital D over little d times lambda 2 minus lambda 1. And that should give me the expression that I'm looking for to determine what the difference in positions of the third bright fringe is going to be. Now, if you wanted to plug in a few numbers just to take a look at what that looks like, then we can do that. If you take a couple of fairly typical spacings I mentioned at the beginning, that D is usually around a couple of tenths of a millimeter, so let's assume a half millimeter, 0.5 millimeters. Let's take capital D to be 2 meters, and lambda 1, let's go 480 nanometers, lambda 2, 600. All right, so 480 is a turquoise, and 600 is kind of hitting in the reds, maybe an orangey red, or something like that. If I plug these numbers in, the units from capital D and little d maybe would tend to cancel, right? And I'd be left over with the units of distance from the wavelength. So whatever I want to find my position difference in, whatever units I want, I should just change the wavelengths to those. Or vice versa, if I want to cancel these with these and leave those, that's fine too. I mean, whatever you want to do. But just to take a quick look here, let's suppose that we plug this in, we're going to get delta y3 as being 3 times, let's suppose that I'm going to cancel out millimeters with the d, so I'm going to go 2,000 millimeters divided by a half a millimeter for the capital D and the little d. And let's multiply that by lambda 2 minus lambda 1. And since those are nanometers, I can put them in 10 to the minus 6 millimeters. Okay? Normally you would put 10 to the minus 9 meters here, but if I want my delta y out in millimeters, then I might as well just leave the wavelength in millimeters. All right, so I'm going to calculate this number, and it's going to turn out to be something. This is going to be a number on the order of 12,000. And this is going to be a number on the order of, that's 120 times 10 to the minus 6. So that's 12 times 10 to the minus 5. times 2 millimeters, which is 1.44 meters. Okay, so it's changed by 1.4 millimeters. And that's not out of the realm of possibility. I mean, remember, these wavelengths are really small, the spacing's really small, the pattern is it takes up very little room, okay? So a difference of a millimeter or so when you change wavelengths, well, that's not out of the realm of possibility as we go forwards. Alrighty. Okay, so in doing this example, we have also gotten the ability to figure out not only where the fringes are, right, in terms of the y, our approximate value for the y here, but we also have, as from last class, we know how to figure out what type of interference is going to happen based on how many wavelengths fit in the path length difference. We now can figure out how many fringes we're going to see. We can figure out where they're going to be. Let's deal with the intensities of them now. Take a look at what the intensities of these things look like. Now, the intensities are due to, I mentioned this a little while ago, what we typically measure is going to be the electric field. Okay, so when I'm thinking about setting up something to detect light waves, the detector is going to essentially be an electric field detector. That means that when I think about the interference of the waves, I think about the electric field amplitudes as they add and subtract, and now the electric field is a vector. It's a vector field. So what we're going to have is a net electric field amplitude at the point on the screen, and then we're going to convert that into an intensity. Now, the intensity is essentially proportional to the square of the electric field amplitude, and you wouldn't know this necessarily unless you've had 4B, but the intensity is proportional to the square of the electric field amplitude like so. And therefore, what we can do is try to figure out what the pattern looks like based on the interference of the two electric fields vectors, okay? So if, for example, we look at constructive interference, then we're going to say the two electric fields are going to be adding completely in phase. Okay, so the E field amplitudes add. And you might say, oh, well, I have an E field which looks like this, and an E field which looks like this. So here's E1, and here's E2. And I'm adding these two things together to get a total electric field value. Now, we're going to assume that the light that is illuminating the two slits is coming from the same source. So not only are they going to be coherent, but they're also going to be essentially the same amplitude, right? It's the same light, same wavelength, but they're also going to have the same amplitude. So that the net electric field is the vector sum of those two, right? And then I look at the magnitude. This is 2, say E. Oops, this is a vector, so we'll leave that out. This is 2E, I'll call it whatever, E naught, E1, E2, whatever, like this. And it's going to be a full value, right? So when I square this, now the intensity is now something along the lines of 4 E squared. And if I look at E squared as an intensity of the light coming through, right? I could call this as 4 I naught. incident intensity. So in other words, consider I naught to be emitted from each of the two slits, going out like that, right? So in other words, you can imagine that when you're coming, I got an I naught coming out through here, I got an I naught coming out through here, all right? So the intensity at a constructive interference maximum is 4 times what you would get from one of the slits, okay? If I think about the destructive situation, there should be 0 intensity there, okay? So in that case, am I doing anything different? Well, no, I'm really still taking electric field vectors and I'm adding them. It's just that in the destructive case, instead of adding them like that, I should be adding like this, right? So that I'm getting nothing from the addition of these two. Now, we can think of a way to do that. Yeah, nice little trig trick, okay? So imagine that the angle between these two is some angle, right? If I draw these, say, let's put this over here. If I draw these like this, I'm going to make them a bit bigger up here. So here's E1 and here's E2. And I think of an angle between these two things, okay? Such that I might measure, well actually maybe I do want to do it this way. If I do this, E2, if I think of, say, this angle here, call it phi, or something like that, right? The angle between two parallel things is 0, okay? In this case, phi would be equal to 0. If it's this way, E1 that way, and E2 this way, then maybe you could see that phi would be 180. Right, or pi. So there's a nifty little way to do this because the trig function, which tells us I'm going to get a maximum when I'm going to get a 0 degree, and I'm going to get a minimum when I get 180, okay, is the cosine. With a difference though, right? So if I imagine I take the cosine of 0 degrees, I'm going to get a maximum in the cosine. If I take the cosine of 180 degrees, I'm going to get minus, right? And what we can do is actually think about, all right, what I want with interference when this is happening, right, is a cancellation. So if I think about cancellation, I'm not going to get it if I just use the straight cosine of the angle. When I want 0 amplitude, like in a destructive situation, if I took half of this, it would work, right? So if I took cosine of half of the angle between the two electric field vectors, then I would say that would seemingly solve my problem, at least here, right? So suppose that instead of using the angle itself, I'm going to use 1/2 of the angle, because now I'm going to take the cosine of 180 over 2, which is 90, and that's going to be 0, and that's going to be my destructive situation, right? That's going to be the one that's going to give me this. Whereas when I have them dead parallel, it doesn't matter if I divide this by 2, okay? So what we can do is we can arrange an intensity expression such that the intensity I at some point at some point on the screen, I'll just call it sub D here, is, turns out to be 4I0 times the cosine squared of 1/2 of this phi angle here, where phi is that angle between the electric field vectors. Okay, we're going to square it because ultimately, remember, this is part of the E field description, so it's squared in the intensity expression here. All right, so I'm squaring, right? Like I'm getting 4I0s here. I'm getting a cosine, and I'm squaring the cosine, and that's going to give us the ability to talk about what the intensity on the screen looks like. Okay. If I plot that as a function of the cosine, right? Let's take a look at what's going to happen. So I'll go back and draw out the initial two-slit situation again. We'll have, okay, I'm not going to draw the light, but assume light's incident here from the left side coming in like it was before. And here is the screen, and I'm looking at what does the screen show in intensity, okay? What does the screen show? Well, it shows a pattern of situations in which the intensity is reaching 4 times what is coming out of one of the slits, right? So there's an I0 coming out here, and there's an I0 coming out here. The pattern is reaching 4 times that intensity, and then dipping down to 0 as it would go to the destructive case, all right? So in the central region here, right, here's my central, there's 0 path length difference in the central, so I should be at a bright spot here. I'm going to go down to a destructive minimum at some point on either side when the two electric field vectors are oppositely aligned, and then they're going to slowly rewind themselves like this, and then they're going to go out to a situation in which they are equally intense as the central bright fringe. Okay, so it should look something like, maybe I missed that and it should have been here, like that. Like this, where this intensity here is 4I0. Okay. So you might ask yourself, well, doesn't this violate energy conservation? How am I putting in I0 through each of these two slits? But I'm ending up with 4I0 here in the central, and in fact, in every other bright fringe, I'm getting 4 times the intensity that I'm getting out of one of those slits. True, but remember, we are also getting destructive interference. So we are also getting 0 intensity here. And therefore, if we average the intensity, the average intensity of the cosine squared would be 2I0, and that's exactly what we're getting out of the two slits. All right, so let's take another look here at an example in which the sources are separated and we have a screen that's a little bit on a different side. So let's take a look at this situation here. Where suppose I have a screen out here. And I have a detector up on the screen out here. So I still have all of the same types of quantities. I still have a distance between sources, which is essentially the same thing as distance between slits, right? These two slits are acting just like sources. And I have a distance from the slits to the screen, so I'll call this little d and this capital D, and then the distance up the screen is still going to be y, all right? So let's imagine that we have these two sources, and I have a situation in which I have my detector at the exact same distance. I know I've drawn it a little bit out of proportion here, but let's suppose I have my detector exactly at the same distance as the two sources are apart from one another. So what that means is when I look at the signal that's going to reach that point, I'm going to be looking at something that has a path length difference. Okay? Path length difference is going to be this much right here. Right? That's the path length difference. And that's the thing that's going to determine what kind of interference we're going to have. Okay? So, let's suppose that we know these distances in terms of the wavelengths. Let's suppose that little d is 6 lambda and capital D is 20 lambda. All right? Such that this is also 6 lambda of a y position up here. All right? When the detector is that far, what kind of interference am I getting? Maybe we would wonder, what is the path length difference and how to find that? And how many extra waves might I have in the path length difference? So there's a couple of ways to do this. One of them is to just simply, because I have reasonably good trigonometry here, I have a good geometrical setup, let's just try and see what we can do in terms of taking the difference in the paths. Okay, I have a right triangle here with the hypotenuse of the path from source 1. I have another triangle here whose hypotenuse is going to be the path from source 2, and those are both right triangles. And the sides of these things we know. So what we can do is, in order to try and determine the path length difference, I might do something like L1 minus L2. Right, where this is L1 and this is L2. These are the hypotenuses of these triangles. All right. So I could calculate what this is by using Pythagorean to figure out what the hypotenuses are. Right? Now L1 is going to be a situation where I have little d as this leg, and then little d plus capital D is that leg. Therefore, L1 is going to be the square root of the sum of those squares. Little d squared plus d plus capital D, that's squared. And it's the same essential thing here with L2, except I don't have this little d as part of the lower leg. It's just little d and capital D in L2 here. So it's the square root of little d and capital D. Like so. If we're interested in what that path length difference is, I could, at least in terms of the wavelength, maybe I have no idea what the wavelength is, but in terms of the wavelength, I could figure out what the path length difference is. This is still going to help me figure out what kind of interference I'm going to get at this position y, because it's going to tell me how many extra wavelengths should I be expecting in the path length difference. And I have a clue that if I have an integer number, well then this is going to be construction. If I have an integer plus a half, then this is going to be destructive interference. If I have something in between, it's going to be maybe slightly constructive, if you like, or it could be slightly destructive if your glass is half empty. So, we're going to go and take a look at that. If I calculate these numbers, then I'm gonna find that this lambda, oh, I'm sorry, this D is 6 lambdas, so that's 6, and then this is gonna be 26, and this is 6, and that's 20. So when I calculate all this out with 6 and 20 in it, I get a number that's 5.8. 5.8 lambdas. You might ask yourself, what kind of interference is that? Is that constructive? Is that destructive? Well, let's do this. I'm going to look at it in terms of wavelength, and then we'll look at it in terms of phase angle. All right. In terms of wavelength, I already said that if it's an integer number of wavelengths, then it would be constructive. And this is pretty close to 6, but it's not 6. If it was an integer plus a half, it would be destructive. This is close to 5.5, but it's not 5.5. It's closer to 6 wavelengths than it's closer to 5.5 wavelengths. Therefore, this should be halfway between, but a little bit more on the brighter side. All right? With 5.8 wavelengths in the path length difference, I should be expecting a bright spot, but not a fully maximum bright spot, right? It's going to be halfway between the brightest and the 0 spots, but even past the halfway point just a touch, right? Now, I also want to be fluent in thinking about where is this in terms of phase angle between the two waves, right? So if I take this 5.8 wavelengths number and I divide it by pi, I'm going to ask what multiple of pi is this? So let's go back and try to set up what we expect. In terms of wavelengths, I know if it's an integer number of wavelengths, then I should get construction. What does that translate to in terms of phase angle? Well, with the electric field vectors, it means they have to be parallel. If I'm expecting construction, they have to be parallel, which means the phase angle has to be a multiple of 2 pi, right? If I'm expecting destructive interference, then I'm expecting a phase angle of pi, and therefore that would equate to integer plus a half of a wavelength difference, okay? So if I divide this by pi, I'll find out how many pi's is it, okay? This translates to about 1.6 pi, all right? Now, that number 1.6, and we should be able to make the same exact argument that we made with the 5.8. If I'm expecting construction, I would expect 2 pi here. It's not. It's less. But it's not as low as 1 pi, right? It's between the two. 1.5 would be right between, and 1.5 pi, remember, would not be destructive interference. That would be partially constructive interference. It would be exactly halfway between destructive and constructive, but it's a little bit past the halfway point. So this tells you that given a phase angle, we should also be able to interpret what is the interference that we're getting. Is it constructive? Is it destructive? Is it in between? Approximately where in between is it? All right? We'd be able to make those determinations from both the wavelength number and from the phase angle number. Okay? All right, good times with that. I think that is going to essentially finish off what I'm going to talk about in terms of two-slit interference, and I would encourage that you be very solid on assessing the path length difference, determining how many wavelengths fit in the path length difference, and then understanding how to use the small angle approximation in the double slit experiment so that you can then find things like the position of the bright fringe or dark fringe that you're interested in on the screen. Okay. So that being said, we're going to move on to the third type of interference that or the third cause of interference that we were going to get. I've talked about 2 of them so far. We've talked about path length difference, which was this one. That was actually number 2. And we also talked about wavelength difference, okay? So when we started this, we did the two examples of glass blocks with different indices of refraction, right? So one of them has an index and the wavelength goes in. It changes while it's inside the index material. It changes back to its air value when it leaves the glass block. If I have a different glass block underneath, there will be a different wavelength change inside that block, and therefore the number of wavelengths that it travels will be different from the one in the top, right? So our causes for interference were, number one, that if you had a wavelength in a material, the wavelength was reduced by the index. And that turns out to be lambda divided by n. So the lambda that I'm talking about here, I can put a sub naught on it here to let you know that it's, for example, typically what we would do is we would cite the wavelength in air, because that's what we're used to, okay? So we'd say, oh, I have a 550 nanometer beam here, and it's gonna go into water, or it's gonna go into glass, or acrylic, or whatever. And that's gonna reduce its wavelength, okay? So that's one cause of interference if I have two different materials of different index, okay? The second one is the path length difference, which I just again abbreviate the PLD. In other words, if I have two wavelengths in which they are completely, two wavelengths. If I have one wavelength and two beams with the exact same wavelength, all I'm doing is making one travel a little bit further than the other, and that's going to cause a shift in the wavelengths by the time they are, that's not a shift, it's going to cause a difference in the wavelength in the cycle when they meet each other on the screen. So that's the two-slit interference. Number three here is reflection. Reflection off a material will change the phase of the wave, okay? You can often see this very easily with a mechanical wave. So if I take a string and I attach it to something rigid and I wiggle the string, if I go with one up pulse like this, the pulse is going to go in, but if it hits this thing and then bounces off, it's going to be underneath when it comes back. I encourage you to try that out at home. But when you start the pulse as an up pulse, if you're holding on to it, and this is what's called a fixed end, what's going to happen is that up pulse is going to go in, hit this thing, and come back inverted, okay? So the reflection happens at a boundary. So that if I have a boundary here between two materials of different index, and I have a wave coming in here, and I realize I'm drawing this only as a beam, just imagine there's a wavelength on here. It's going to reflect, and we know that the angle is going to be the same, the outgoing angle should equal the incoming angle and all that great stuff. And it could be polarized based on Brewster's angle. We've got a lot of info about reflection, but here's one more. If it's going to reflect off a material whose index is larger than the one it started in, then there's going to be a phase shift. If it's going to reflect off a material whose index is lower than the one that it started in, there will be no phase shift. All right, so I'll summarize that here. Basically, if N2 is greater than N1, or if N2 is less than N1, like this, okay? Then what's going to happen is, if N2 is greater than N1, then we're getting a shift, okay? What that means is the wave is coming out on the reflected side, flipped upside down from how it went in, okay? So I'm just gonna call that the phase shift of pi. All right? If N2 is less than N1, so wait, back up. This is a situation that basically happens almost all the time. Light comes from air, air has an index which is basically 1, and it goes and reflects off any other boundary, right? The only situation in which this wouldn't work is if it was reflecting off vacuum. Vacuum's index is 1.00000, whereas air is 1.003, okay? Any other material, glass, water, etc., when it reflects, it comes off with a phase shift. All right, so that's because the index of the water is greater, the index of the air is lower, so this comes off with a phase shift. If it's the other way around, if you are immersed in water and you're looking at the beam bouncing off this way, then it would be bouncing off the index of the interferent, dang it. You're bouncing off the boundary between water and air, but that index is air and it's lower than water, and therefore I will get zero phase shift in that sense, okay? So phase shift 0. All right, now, when you have zero phase shift, that means the wave returns in exactly the same, or it bounces off at exactly the same point in its wave as when it hit. Whereas in a PHYS phase shift, it's bouncing off and then coming out a full half wavelength different than the way it went in. So you can probably see now why this causes interference. If I have two beams coming in and I have one that goes into this material and bounces off and comes out, then I'm going to have two beams here which could interfere, two waves here that could interfere, and I have to assess their phase shifts. Okay. We do have such a thing happening all the time, and it's known as thin film interference. In fact, thin film interference takes into account all three of these. Okay. So let me just diagram this out for you. A thin film is a situation in which I have for example, a thin, maybe like water on glass or something like that. So here's a thin film of something, and it's on top of this other thing. Or you could even go to the other part of it, which is the thin film when you think of a soap bubble, right? There's a thin film of water surrounded by air on both sides, right? That'd be a thin film of water. For this one, let's just assume I've got something like a thin film of water on top of glass. This is air here, this is water in here, this is glass down here. All right, the index of each one of these, we know. The index of air is 1, the index of water is 1.33, and the index of glass is 1.5. Since there's reflection at every boundary, suppose I look at incident light. Now, I'm going to caution you here once again. I am only going to examine normally incident light, okay? I will not, however, be drawing it normally incident, because if I did that, you won't be able to see. I'm just going straight in and straight out, and you won't be able to see what I want you to look at, okay? So this is going to be at normal incidence. Even though I'm not going to draw it that way, all right? So imagine here, I've got this situation going. I've got a beam of light coming in, a wave of light coming in like this, okay? But I'm drawing it at an angle. We have to think of it as coming straight in like this, okay? It's going to bounce off like that. That's my reflected beam, reflected wave. And we can say right away, wait a sec, that went from an air index into a water index, right? It went from air index into water index, therefore it should be coming out with a pi phase shift. So I'm going to mark plus pi on that one. Now, this is water, which is transparent, so some of the light's going to go into the water. It's then going to come in here, bounce off, and then come out like that. Let me move this plus pi up here. It's going to bounce off the glass interface. The glass interface also has an index which is larger. It's 1.3 to 1.5. Therefore, this one comes off with plus pi also. Okay? Now, consider we're not done. We've just started. I've been able to assess the reflection phase shifts, but what else is going on here? I certainly have a path length difference here. The second ray down here traveled a little further than the first one up here. So I have a path length difference. This is why I'm considering normally incident light only, because I don't want to deal with coming in at an angle and going out and dealing with that path length. Okay? So let's just call this length, I'm sorry, let's call this thickness. What do you want to call the thickness? I want to call it T. Let's call it T. Okay? So the thickness, it undergoes two thickness travels in its bouncing off of the lower interface down here, and then re-emerging out into air. Okay, so there's a path length difference. This one also, plus a path length difference, which is equal to 2t. Okay? So now we have to assess, okay, how many wavelengths fit in the path length difference? But wait now, there's more. It's in a material with an index. Therefore, its wavelength is reduced. So I cannot figure out how many wavelengths fit into the path length difference as if it was in air. I need to do it as if it's in water, because that's what it's in. So it's not only plus the path length difference, it's plus lambda naught divided by n inside the material. So this is all three of the causes of interference going on here. Okay, so we're going to have a lot to deal with. With the two-slit interference pattern, because we had it in air and all the wavelengths were the same, and the only thing that we were concentrating on with path length difference, we were able to figure out a set of equations that told us, oh, this is constructive situation, this is destructive situation. You cannot do that with this until you figure out what these two relative phase differences are. Okay? So the way I think about this, and we'll do an example right here, the way I think about this is the first thing to do is figure out, okay, what's the relative phase difference of this compared to this? All right? Now, what I think in my mind then is, do they come out with the ability to construct or destruct? Then I put in the path length difference and I put in the wavelength reduction, okay? With the idea that they're coming out either ready to construct or they're ready to destruct, okay? Now, what I would consider in this case is because they both came out with the same phase shift, I would say if nothing else happens, they're going to construct, right? Because they both shifted by exactly the same amount. That's basically like nothing happened. Now we have to figure out, okay, if it's still going to construct, then this path length difference down here has to fit an integer number of wavelengths. If it's going to destroy, then the path length difference has to fit an integer plus a half number of wavelengths. All right? Therefore, you see how you can't figure that out until you know what the phase shifts are, right? I don't know what's going to happen with the path length difference and the relative stuff down here with the wavelength reduction until I know what's happening up here. At least that's how it works in my head. Some of you might be wondering, well, what about the last wave of light which goes into the glass? Yeah, it goes into the glass, but the glass is big enough that we're not worrying about reflection off the bottom. We're just worrying about what's reflecting off the thin films. Okay? So this is what we're concentrating on, and then this we're kind of throwing away and not worrying about. All right. Now, on the other side of that, imagine that this was air and then the soap bubble film and then air again. Then I'd have a situation where air to water gives me a plus pi, but now water back to air gives me a 0. So I would then have tended to say those two are more ready to destroy each other. And therefore, if I want construction, I have to have a certain situation in my path length difference, an integer plus a half, in order to get them back in phase. All right. So let's take a quick look at an example here in which we're going to calculate, we have two wavelengths, and we're going to calculate the thickness of the layer. All right. All right. So let's do this. So I want to find the thickness of the layer. Same situation as what I just erased, but I'll redraw down here. Okay. Again, remember that these are always going to be at normal incidence, even though we're going to draw them this way. All right, so what I have here is the index out here is air, the index here, and 2 is 1.25, and the index here is 1.5. Okay. Our goal is to find the thickness. With the idea that when I shine wavelength of a certain, light of a certain wavelength, I get destruction, and when I change the wavelength, I get construction. Okay, so let's suppose that with lambda, let's suppose that with one wavelength, lambda 1 here, lambda 1 gives construction, and lambda 2 gives destruction. And we know what these wavelengths are. Okay. This is basically this is the model of the phenomenon of rainbows on oil slicks. Okay, we're going to look at the oil slick. You're going to see the little rainbow, and this is kind of why it's happening. Okay, so let's take a look at construction. Because of the indices of these materials, I know that both of them are coming out with a pi phase shift. Okay, therefore, my constructive situation here, when I have both of the waves having a phase shift, my construction then just goes back to, okay, I have to assess the two other interference causers. I have to assess the path length difference and the wavelength reduction. All right? So the path length difference is 2t. If I want construction, then I would have said there's an integer number of wavelengths of lambda 1 in the path length difference. But remember, lambda 1 has to be reduced by the index, all right? So this has to be m times lambda 1 divided by n2. All right, where now I would say destructive interference, what I would get is that path length difference again, but now in order to get destructive interference in my path length difference, I need to have an integer plus a half wavelength, okay? And that's lambda 2, which is giving my destruction divided by n2. And so ultimately, what we can do is I can take this condition here, solve for t, and you'd say, well, what about m? We don't know what m is. Fair enough. But we know that it's an integer. And it's not going to start at 0 in this case because 0 means there's no thickness. So it has to at least start at 1. I'm going to put in 1 here and then figure out a thickness. And then I'm going to put in 2 and figure out a thickness. And put in 3 and figure out a thickness. And 4, etc., etc. So I'll get a table, or I'll get a set of values of thicknesses for which constructive interference would happen for this size wavelength. Then I would go to this condition, and I would do basically the same thing. I would solve for the thickness, and I would say, okay, in this case I can use a 0 because I'm going to have a half wavelength difference in the path length, half wavelength in the path length difference. So I can start at 0 here and say, okay, I've got a 1/2. And I'm going to go to 1, calculate the next thickness, 2, calculate the next thickness, 3, calculate the next thickness. And then at some point I should get a thickness here that matches a thickness here, and that's going to be the minimum thickness that satisfies both of these situations. Okay. So just to give you an idea of how to do that, suppose that lambda 1 is 700 nanometers and lambda 2 is 600. Okay. I know what the index is that I need here, and so in order to find the thickness, I can go in and start saying, okay, at my first construction, I would have an m equal to 1. So at my first construction, I would have an m of, let's see, I did this out here. So I would have an m of 280 nanometers. This would be my thickness, right? That's for n equal to 1. Well, let me make a full table here for you. Let's do this. T is in nanometers. So when n is equal to 1, this is equal to 280. When this is 2, let's see, I just knocked these out here, 560, 840, 560, 840, and 4 is 1080, no, 1060, no, 1020, hold on a second, 1020. No, that doesn't seem right. No, it's 1080. Yeah, that's right. It should be 1080. All right. So this is putting in m's and solving for t's. I'm going to do the same thing down here. My m value and my t value. So I can start with 0 in this case because I've got the half wavelength in the path length difference. So if I start with 0, I'm going to get 120. Let's see here, what do I got for my values here? 120, 360, and then I had 600 and 840. All right, so you can see here that the minimum thickness that satisfies both of those wavelengths conditions at these wavelengths, giving the construction or destruction, solving for the thickness, the common one is 840 nanometers. So that means that I have to have a layer of 840 nanometers thick here on top of this stuff, which is apparently glass, in order to construct this wavelength, but destroy this one. Right, so that literally means at normal incidence, I wouldn't detect red light if I was shining it in, or at least phased red light of 600 nanometers. Okay. Great. Well, that's how thin film interference works. Remember, it's based off all three conditions. It's based off the wavelength reduction, right? You have to have this in here. It's based on the path length difference, right? And 2t because it's normally incident. And it's also reflective, and that means you have to assess your phase shifts. So in terms of a problem solving strategy, it should be, for me, it's going to always be phase shifts first. Then I can write down what the interference conditions are going to be. All right? Great. So far so good. And I think what we're going to do now is we will finish off a little bit more on thin film interference. We'll look at some extra situations beginning tomorrow, and that should finish off everything you need for the homework. And so we'll stick with Thursday being the homework due and quiz day. Alrighty, so usual deal with those in the sense that homework is due by midnight those days, and quiz will be open and available until midnight. So I will say happy day and good luck for the rest of this day, and I will see you tomorrow for a little bit more on interference.